Salts, lecture number 24. So if you remember back early in 112, or not, well, excuse me, not 112, 111, early in, that's when we talked about defining different reaction types. When we had defined an acid-base reaction, we said that the things that are produced when an acid reacts with a base is some salt, some ionic compound, and water. So these ionic compounds, these salts, are what we're going to talk about now. It's the conjugate of an acid or a base, right? So if these acids or bases that we start with are weak in strength, then the conjugate, this salt that's produced, is going to also be a weak acid or base, right? So we're then going to be able to treat these as being able to undergo equilibriums as well, right? So these salts that yield acidic solutions are typically highly charged metal cations, and the anions of strong acids yield an acidic solution. So for example, we have iron nitrate. It's going to give us an acidic solution. Or we can take something like a weak acid, HF. If we take sodium fluoride, that, because F is the conjugate of that weak acid, it is going to be a weak acid base as well. Weak bases are salts that are an anion of a weak acid and the cation of a strong base. Like I just talked about. So here's another one. The acetate, sodium acetate. The acetate portion comes from acetic acid. It's the conjugate of a weak acid. The NH is the conjugate of a strong base. So the acetate can react with water to form OH minus, to reform that original acid. So we're always going to have these acids or bases. Typically, these salts that are going to affect pH are typically going to be the combination of a strong acid and a weak base, or a strong base and a weak acid. Right? The resulting, one of those ions is typically going to be a weak acid or base. Right? If you remember when we first talked about these equilibrium expressions, if we can add up two equations to get a third, then we can manipulate the equilibrium constants to calculate a new equilibrium constant. So if we look at the strong acid, HA is in equilibrium with H plus and A minus, and then that A minus, if HA is a weak acid, A minus is going to be a weak base, so it can react with water to form OH minus and HA. So that top one is an acid dissociation, or Ka. The bottom one is it acting as a base, or Kb. If we add those two reactions together, we're going to see we get H2O is in equilibrium with H plus and OH minus, which is our Kw. Right? So if we add the two reactions together, we end up multiplying the equilibrium constant. So Ka times Kb is equal to Kw. Right? So we can then, if we have a salt of a strong or a weak acid, which would be a weak base, we can solve for its Kb by taking Kw divided by Ka. Or if we have a weak acid as the conjugate of a base, we can take Kw divided by Kb to get Ka. Right? So we can these salts or base pairs are related both in strength, but also through this expression Ka times Kb is equal to Kw. Right? So once we have these new K values, we can solve these equilibrium values the same way we've done every other thing, right? We just have to set up our equilibrium, determine our actual equilibrium constant, what its value is, the equilibrium expression and its value, and then we can solve whatever value using an ice table. So we're not spending a lot of time here in the lecture talking about going through these problems because the process is the same. The hardest part for a lot of these is defining our equilibrium system and what the value of that equilibrium constant is. Right? Once we define that and what it's related to, then the approach we take to solve the problem is going to be the same. Right? The last type that we can have is a combination of if we reacted a weak acid with a weak base, the salt that we produce is going to be a combination of that conjugate of weak acid and weak base. So something like if we take NH4 and CN, NH3, and react it with HCN, we're going to get NH4CN. One of the conjugate of the weak base, ammonia. The other is the conjugate of the weak acid, HCN. So both of them can act as an acid and a base. So the pH, if you want to follow it that way, we can calculate the Ka values for each one of those by dividing it by Kw. Right? You see both of them have a K value. The Kb here is going to be larger than the Ka for the NH4, so it is a stronger base. So this NH4 or CN is going to be a basic solution. This process is going to dominate over this process because of the size of those equilibrium constants. Right? Mathematically, these are more difficult to solve. Typically, one of them is going to dominate. We're going to ignore the other process. We probably won't do, honestly, very many of these calculations because of the complexity. I just want you to be aware of them. The last thing that we should talk about is a third definition of acids and bases. So if you remember our first two definitions again, the Arrhenius acid is a substance that produces H plus or OH minus in water. The Bronsted acid is a proton donor. Right? Both of these definitions involve this H plus or this proton. Right? There's a completely other class of acids and bases that don't involve hydrogen at all. Right? It's the most general definition of these acids and bases, and that's defined by Lewis, the same person who came up with the Lewis structures. Right? We can take his approach to define these acting as acids or bases, and when you do that, what we're transferring isn't now the proton, but a pair of electrons. So a Lewis acid is a substance that accepts a pair of electrons. A Lewis base is a substance that donates that pair of electrons. So this is the most general definition of all. It's the least restrictive. We're only looking at transferring electrons. So if we look at water then, the autoionization of water, if you look at it in reverse, the H plus is going to accept a pair of electrons that it's going to share now from the OH minus to form the water. So the H plus is an acid, OH minus is the base. Something like if we look down here, those same definitions, everything we called before an acid and a base, we're still going to call. This just opens up a wider range of compounds that we can consider acids and bases. Right? We're going to talk generally about three different types of Lewis acids and bases. The first one is being this electron-deficient molecules can be Lewis acids. Excuse me. So boron and aluminum typically violate the octet rule, remember, because they can have fewer than 8 electrons around their center and they still have a formal charge of 0. So these two are then capable of accepting a pair of electrons. So they're going to act as Lewis acids, right? As in this example here. The next one, Lewis acids with polar multiple bonds. Right? So if we look at molecules that contain polar multiple bonds can also function as these Lewis acids because those pi electrons, they can then donate or accept, they can be used to accept a set of bonds by moving that out. So if we look at SO2 here, if we look, remember its Lewis structure, excuse me, we have, this is a polar molecule that has double bonds, so the OH, that pair of electrons can be donated to the sulfur, which then those multiple bonds can move out to the oxygen, which can then grab it from the hydrogen. So we get this new molecule formed over here. So if we have an ability to accept electrons, it's going to do that. The last type of Lewis acids are these metal cations, can act as Lewis acid when dissolved in water in this hydrated sphere. So we take the say in a metal that's got a 2+ charge, it's going to be able to accept electrons from the water to form this hydration sphere, forming this new product. Not necessarily think you need at this point to be able to distinguish these three types of Lewis acids and bases. Just be able to define them and recognize them when you see them. Right? A Lewis acid is something that accepts a pair of electrons. A Lewis base donates electrons.